Start recording. All right. Flip it over for that. All right. Let's see. So normally when you guys walk in, I'll have our syllabus up here, and it'll normally show the next week, week and a half. And if something is important that's like grade related, I usually put it in bold. So like turning in your first day packet, obviously you can take extra time to turn in your first day packet if you want. There's our first quiz down there on the, let's see, you guys are even days, so September the 10th. And so you can kind of always see sort of what's coming up. And essentially what you'll want to do is, there it is. You can always kind of look ahead, and you're welcome to take a picture of this if you want. If you wanted this file, where's it going to be? Yeah, on the Google Drive. So how do I get to the Google Drive? I need to just go ahead and post it up here or something, but it's on that first page of like your first day packet. I'm going to borrow yours for just a second. This is for you, not for me doing this, since I've got so many papers and stuff that I touch. So up here on that first page, it has like your Google Drive. But I will go ahead and like post it just so it's like always right over there. If you've got your first day packet and you want to turn it in, you can rip off that first page and just hand me everything else. So if you just hold it up, I'll come around and grab those. Thank you. Thank you. Thanks. Thank you. Thank you. Thank you. Thank you. Thanks. Gracias. Oh, that's fine. I got a stapler over here. Yeah, when you rip off the front page, sometimes it takes the staple with it. Got yours. Thanks, Sandy. All right, anybody else? Cool. If you haven't turned it in yet, some of you guys might have turned it in the past already. But if you haven't, then bring those next time. And actually give you 100 for turning this in. So probably the easiest thing you'll ever do in an AP class. Okay, so I can kind of look at this, and it also tells me what I should do. So today's the 31st. No, it's not. It is the 1st. So it'll tell you like what you could read, things like that. If we're a day behind or something, I have this in your little syllabus that was in your little packet, but if you haven't done 2.2, I would do that first, and then 2.4. Usually the reading, like a section 2.2, is typically like 4 or 5 pages or something like that. So it's not a ton, but it does snowball if you just try to like put it all off until the night before the test. That's typically not a good strategy. So I think that's it before we get started with science. We're actually ready to start real science in here, I believe. Any questions about stuff? Voluntary homework, we got a chance to talk about that last time. Cool. All right, I think we're ready to roll. Let me take roll real quick, just in case my computer decides to unlock itself. Jaden, I'm missing Jaden. And Adela moved to a different class, one of my other AP Bio classes. All right, so I'm missing Jaden. Jaden, second period. All right, okay. So we'll start off, if you've got your notes with you, they look like, I have to bum yours again. They look like this. Up at the top it says AP Biology, Chemistry, and Biochemistry. Okay, right behind you on those stacks. One stack is for my pre-AP classes, and one is for AP. So if you didn't get one, you can go grab one. I actually need one too. I need to reference it for the camera, so I'll grab one myself. Oh, thank you. Appreciate it. All right, so the notes that look like this. I know we're on the small camera right now, but I think you can still see it. All right, so up at the top, it starts off section 2.1. If you were looking at the syllabus, You'll notice I didn't even have you read section 2.1. That's because it's all review, but I do want to walk through it just a little bit with you. So today will be slightly weird because what we're doing is I need you to just know like very specific background chemistry stuff. So it'll be a little bit less cohesive. It's basically like if this is the shelf of all the chapters in chemistry, it's like I need a little bit of that from chemistry and a little bit of that and a little bit of that and a little bit of that. So we kind of hop around a little bit in the beginning. And then when we get to water chemistry, right about there, we'll get to that today. That's when it starts to actually like flow and it should be a lot more cohesive. So I do apologize. I'm basically just kind of picking and choosing the stuff from chemistry from the past that you need. So hang with me. Starts off easy. Matter's made up of atoms. That's pretty good. In the atoms, we got protons, neutrons, electrons. Remind me, where are the protons at in an atom? In the nucleus. What else is in the nucleus? Neutrons. And then where are the electrons at? Yeah, they're in a cloud. Your teacher might have said an electron cloud, or they might have said an orbital, or they might have said electron shells, or they might have said energy levels. All of those are correct. It just, what aspect of it are you looking for? Kind of like those things out there, those called vehicles out in the parking lot. My wife makes fun of how I say vehicle instead of vehicle. But are they vehicles? Yeah. Are they cars? Sure. Are they automobiles? Yeah, so they're all right. Okay, so technically an orbital and an energy level are different though. So in here, we don't care at all about orbitals. We care mostly about energy levels. So real quick, I'm just going to show you what an orbital is, just so you know what an energy level isn't. So we care about energy levels. Orbitals work like this. Let's say I've got the nucleus of an atom, and let's say I'm looking at like helium. So helium on a periodic table is a 2 and a 4. Okay, so first off, what does that 2 mean on helium? What is that called? Yeah, the atomic number, okay. And then the atomic number, what does it actually mean? Yeah, the number of protons. So if I'm looking at this, that means I have 2 protons. What else do I have 2 of? Based off of that number? Electrons. Now, I do have 2 neutrons, but I got neutrons by taking this minus this. So this number down here, what was this number called? Yeah, either the atomic mass or the mass number. Technically, this is a mass number. Atomic mass is when you keep all the digits. So like, for example, carbon, it'll say, hey, Jaden. So carbon, it'll say up here 12.11. That's technically the atomic mass. When we round it to 12 or 4 or whatever, then they call that the mass number. So in here, we generally just deal with mass numbers. Okay, so how did I get that number 4? Like what things did I add together? Yeah, protons and neutrons. So basically, I'm weighing the nucleus. Electrons weigh something, but they're so much lighter than protons and neutrons, we kind of don't count it. So this is protons plus neutrons. Okay, so atomic number tells me how many protons I have. And then here's the thing. I don't know how deeply you guys think about, atoms, so you'll probably laugh at me. But here's the thing that I understand, but I still can't wrap my brain around. Like I can understand jet propulsion and launching people to the moon. They ride around on a little buggy for a while, and then they like come back home. So I get that, but then like I also kind of can't comprehend that, Or what computers can do with some teeny tiny chip, like, oh, we just etch it really small, and you're like, there are billions of miles of teeny tiny gold lines. How do you do that? They're small lines, and I'm like, yeah, but like still, like I get it, but I don't get it. So here's what I don't understand. The difference between like neon, neon, like neon gas in a sign, and sodium. Sodium is a kind of a soft metal that explodes if it touches water. And the difference is this has 10 protons and sodium has 11 protons. That doesn't make any sense to me. It seems like sodium should be made out of different stuff. Like if I have sand in my hand, like, oh, I have 10 grains of sand, so it's sand. When I add an 11th grain of sand, all of a sudden, it's chocolate. Like that doesn't make sense. It just seems like it'd be more sand. So I don't understand how changing, adding or removing a proton like changes something from a gas to a metal that's not reactive at all to something that's like super vigorous reactive. Like that doesn't register in my mind, but I accept it. So helium always has 2 protons. Oxygen always has 8 protons. Is it possible that oxygen can gain and lose electrons? Yes, but it always has the same number of protons. Okay, so now let's look at neutrons for a second. This is kind of odd, and this might be the first thing where you have to think a little bit. The other stuff might be rusty, but like you've heard it before. All right, so here's hydrogen. How many protons does hydrogen have? 1. How many electrons? 1. So it's got a proton and an electron. How many neutrons does it have? 0. Why is that? That's true. So from a math point of view, I've got 1 proton. Protons plus neutrons equals 1, so like I have to have 0 neutrons. So mathematically I get it, but like, why doesn't hydrogen have neutrons? Everybody else on the periodic table has neutrons. Early on the periodic table, let me flip camera views for you guys. Early on the periodic table, if I've got like 2 protons, I usually have like a couple of neutrons. It's almost like a 1-to-1 ratio, close to it. If I've got, 4, then I've got 4 protons, I've got 5 neutrons. If I've got 5, I've got 6. So it's almost 1-to-1. Then as I get deeper down here, like gold, it's got 79 protons, and I can't quite read that. I think that says 197. So it's got 79 protons and over 100 neutrons. So here's my question. Hydrogen, no neutrons. Everybody else, it's kind of 1-to-1-ish. And then as we go farther and farther down, every time you add a proton, you add like extra neutrons. So my question is this: why? Like, why is that the case? You can kind of think of it a few different ways. You could say, why doesn't hydrogen have any neutrons? Or you could say, why does that guy need neutrons? And why does that guy need even more neutrons? What's the function of a neutron? Must have a function. Everybody needs them except hydrogen.
Does it put space between all the protons because all the protons are positive and repel each other?
Nice. It's a good first day. Yeah, that's exactly right. So a lot of times what you hear in chemistry, and I'll repeat that if you're on watching the video. So a lot of times in chemistry, your teacher might say, well, neutrons stabilize the atom. And you're like, all right, cool, I'll accept that. Why doesn't hydrogen have any neutrons? Doesn't it need to be stable? Here's why. Let's say I have something like gold, Au. Gold has 79 protons. What's the tightest space known to man? Like, we're in this room, that's a tight space. We could be in a tighter space. I don't know, this drawer. What's the tightest space known to science? Isn't it like the nucleus of an atom? And what are we going to shove 79 of in there? It's okay, you can answer out loud. Protons. What's the charge on a proton? Positive. What happens when I take 79 positively charged things and shove them as close together as is known to man? What will they do? They will repel. And when they repel apart, that's called an atom bomb, right? I'm made out of atoms and I don't want to explode. So how do I manage to shove 79 protons next to each other without them repelling apart? I put in a neutral spacer. Like that. Neutrons. here I am. Let's say I've got helium. I've got a proton and a proton. If I put them too close together, I'll explode. So I put a neutral spacer, just enough to tone down the repelling, but they're close enough to where the strong force, or however physicists explain all that crap, the strong force keeps them together. So neutrons act as a spacer. Why doesn't hydrogen have any neutrons? It's only got one proton, so does it need a spacer? No. And so that's exactly what you were saying. Again, if you're still trying to figure out what the answer was I don't need any neutrons because I don't need any spacers. Now, at first that seems like trivia. Excellent trivia, by the way. It's a good opening line. You see a pretty lady and you're like, hey, you know why hydrogen doesn't have any neutrons? So give it a shot, see how it works. And if it doesn't work, I'm sure there's always online dating. Okay, so at first this seems like trivia, but it turns out we'll actually use this a lot. The fact that hydrogen is just a proton and electron, we'll come back to that a lot. We'll explain that a lot. Okay, so back to a question I kind of started just a little while ago. Again, we're kind of bouncing around on random chemistry stuff that's important. Orbitals versus energy levels. And again, I don't always go in the exact order of the notes, but I'm usually within like just a few lines. So if you were looking at this right here, we're kind of bouncing around in those top like 3 or 4 lines up in there. Okay, so let's say I take a picture of an atom and I can see some electrons. Do the electrons rotate around a nucleus like planets, or do we know that they do, or do we know that they don't, or are we just not sure? Or like, what are the electrons doing right now? Like, are they moving? Do they stay in the exact same spot? What do you think? What do you think we know, and what do you think we don't know? And it's okay, like I don't expect that you've read this before or anything.
Don't we like not know? They're like everywhere at once.
Yeah, we don't know. Here's why we don't know. Okay, you know how light, if you're a senior and you've had physics, you know how light can kind of act like a wave and kind of act like a particle? It kind of acts like it has mass and it kind of acts like it doesn't have mass. Well, whenever we shine, I'm sure there's probably freaking lasers involved or whatever, but whenever we try to look at an atom and look at electrons, just looking at them with a light or a laser knocks them off course. So we don't know what they were doing before we looked at them. Pretend that I'm walking along like this. I'm an electron walking a straight line. You can't see me. As soon as you shine a light on me, that light is strong enough to push me off course. So anytime we look at electrons, they're always flying directly away from us because we just pushed them that way. So maybe I just stand there and you push me. I would just look like I was flying away. Maybe I'm running in circles and you push. I do this for your benefit. Maybe I'm running in circles and you push me. I'll look the same way. So we don't know. What we do know is this. Every time we take a picture of helium, it'll be like this. 1, 2. All right? Now, let's take another picture and just overlay it. 1, 2. 1, 2. 1, 2. We just keep overlaying all these pictures of helium, and this is what we get. Like that. And so what they'll do is they'll say, hey, that general electron cloud, they'll call an orbital. And this is where we are 95% confident that we will find electrons. Sometimes they're out there and we don't know why. They always seem to come back. We have no clue. So that's an orbital. It's just sort of this general area where you tend to find electrons. You guys messed with orbitals and you had to do like electron configuration. These are the S's. These are the P's, the D's, the F's. 1s1, 1s2, 2s1, 2s2, 2p1, 2p2. You might not have liked it, but are you like, yeah, I remember doing something like that? So those are orbitals. In biology, we don't care about orbitals. We care about energy levels. So an orbital is where you tend to find it. An energy level is how much energy do those electrons have. So electrons and energy levels is what we care about. I bet to explain stuff by the time the year is over, before we ever review anything, just when we're learning new stuff. It's an AP class, so we have some review time at the end of the year. I bet, not counting review, I bet I will draw energy levels on the board 17, 18, 20 times this year to explain stuff. I bet like 20 times I will explain crap with energy levels. Okay, so energy levels. This is where you've been taught some of this stuff, but it might not have like stuck, or you might not have had it stick the right way in chemistry. Sometimes the first time you learn something, you kind of learn it, and then the second time you come back years later and you see it from a different point of view, and you understand it in a different way. So these are energy levels. Your chemistry teacher at some point was drawing energy levels. How many electrons are in that first energy level? Yeah, you can hold up to 2. Now, you heard that so much you probably just memorized it, but how do I know that it's 2? How can I explain, well, here's, if you were a brand new chemistry student for me, or I explain this also to my 9th graders, how can I show them that it's 2? If I give you a periodic table, how can you explain to me that it's 2? Yeah, top row has 2. That first ring is an energy level. That top row is an energy level. How many electrons are available? 1, 2. So that first energy level holds 2. How many does the next one hold? 8. How do I know that? Because the periodic table says row 2, that's ring number 2, holds 1, 2, 3, 4, 5, 6, 7, 8. What about the next one and the next one? And that's when you can start getting into some of these big ones where you're like, well, it holds 1, 2, 3, all those. So that holds however many. So this corresponds with that. How many energy levels? What's the maximum known number of energy levels that you can have? Again, as far as we know. 7. How do I know that it's 7? Yeah, there's 7 rows. So in chemistry, your teacher probably said, like, if you really understand the periodic table, it's kind of a good cheat sheet. You just have to know how to use it. That's what we're doing. So I've got 1, 2, 3, 4, 5, 6, 7 rows. So there you go. I can have that many. All right. Now, what holds these electrons in here is, well, let me just ask you. I got these electrons, and maybe they're flying around like planets, maybe they're not. I'm just going to kind of picture them rotating like planets, even though we don't know that. I got to picture something. What keeps them from just like flying away? Like, say that again? Yeah, the protons. Why is it logical that the protons would keep them from flying away? Yeah, they're opposite charges, so they attract. So the reason that these electrons, again, we don't know that they're rotating like planets, but we'll pretend. The reason these electrons don't just fly out of orbit is because they're attracted to those protons. It's not gravity, to be very clear, it's not gravity, but it's kind of like gravity. It's sort of like, why doesn't the Earth fly out of orbit? It's attracted by gravity to the sun. Why doesn't the moon leave the Earth? There's enough gravity from the Earth. So, like that. Again, this is not gravity. Okay. However, those electrons are attracted to this. Right? They're attracted to that nucleus. Is this pin attracted to the Earth? With gravity, is it? Yeah. Okay, so it will always fall towards the Earth. I'll try it again. I verified my experiment. Okay, so that will fall to the Earth. Electrons are attracted to that, to the nucleus. Okay. Now, let's say I have some electrons around here. So my first energy level is full. Now I can start filling up my second energy level. Okay. When I walk outside, and I've got on a dark shirt versus a light shirt, which one's going to feel hotter in the sunlight? The dark shirt. So why is that? This will relate to bio in just a second, by the way. You're like, I feel like we're learning all this random chemistry stuff, and I've never heard him yet mention an animal or a plant or a cell. So why does my dark shirt feel hotter? Yeah, it's absorbing energy from the sun. But what is absorbing? Like, what do you mean absorbing? What exactly, like how? Like attracting?
Yeah, like the black makes all the light come towards it.
Okay.
Right?
Well, from a physics point of view, you guys are basically kind of getting at like a dark shirt. Like if I have a black shirt, it's absorbing all the colors. You know, this one's blue, so it's reflecting blue and absorbing the other colors. But why is my black shirt hot? Like if you walked outside, Zenny, your black shirt would get really, really hot. But under this light, it's not. It's not like, oh, you're really warm because you're wearing a black shirt under this light, and if you had a light shirt, you'd be fine. So what's actually happening that makes my dark shirt hot?
Is it because it's the absence of color, so then it's absorbing all the color?
It is absorbing all the color, but like how, when I'm wearing my dark shirt, what's happening out there so that I absorb and it becomes heat? And here I'm absorbing all the color if I have on a black shirt, but it's not hot. This is not hot. My car outside is black. It's going to be like blazing hot. That's light and that's light. I know that there's different wavelengths, but like, what's actually happening that's making it hot?
The sun has like heat energy and that light doesn't.
That's true. The sun, you're like, well, that's a ball of fire, and I can probably touch that with my finger. Okay, let me ask you another question. So, pause and hold that question. So right now in your brain, you're like, all right, he talked about energy levels, then he paused and asked us about the sun. Do any of y'all have those little star things? Maybe when you were a kid, or maybe you still have them, and you'd stick them on the ceiling and the walls in your room, you'd turn on the lights, and then when you turn off the lights, they would glow. You could buy little planets and stuff. Even if you don't have them, you've seen them, right? How does that work? I'll give you a hint. It's the same way that the sun works on making my car hot. It's exactly the same explanation.
Not specific enough, but energy?
It is specific enough. It is with energy levels. What if, so where are these electrons attracted? What's attracting them? The protons. Okay. So now, back to the Earth analogy. I've got this pen. What's it attracted to? The Earth, or the ground, yeah. The floor, however you want to say it. So right now, which pen has more potential energy? The pink one or the purple one? The pink one. If you've had physics, it's like potential energy is mgh, mass times gravity times height. So this one has more. If this is twice as high, it has twice as much energy. Right? If I drop this one on my head, I'll feel it. If I drop this one on my head and it's higher up, it'll hit a little bit harder. What if this electron moved up in energy level? What if it went from energy level 2 to energy level 3? Is it stable up there? No, because the rule is you always fill in an energy level. Once it's full, then you can add to the next one, then to the next one. So it went up in energy levels. But again, is it stable there? No. So what will it do right away to become stable? Yeah, it'll drop back down. It fell down, right? Closer to the thing it's attracted to? So didn't it just release energy when it fell? Watch this. There you go. I raised it up. It absorbed energy. It released energy. Almost caught it. By the way, I'm an overreactor. That wasn't bad. Quick aside, give you a little bit of a brain break and we'll come back to this. At one point, Chili's, like they would give you, you know how Chili's gives you like plastic mugs? You don't have to order beer, they serve you in plastic mugs. Those used to be glass, like years ago. And one day they changed and they didn't tell me. So I got my Sprite or whatever, and they give it in the mug, and I go like this, because I'm an overreactor. If you get like, you start drinking an ice water, has this ever happened to you guys? You're like drinking your ice water, and then you're kind of watching the ice like it might just slide down all in your face, so you don't want it to do that, so you kind of catch it at the last minute. You guys are probably smooth, so you guys probably do something like this. You're like, not me, I'm an overreactor. So I'm like, like that, and I spill everywhere, and I make an idiot out of myself. If the coffee's super hot, and I know it's super hot, and I'm just going to take a little sip, even though I know it's hot and it's like super full, you're like, oh, that's hot. I don't. I freak out. I'm like... So normally when I start to drop something, I'll like make a total idiot out of myself, and instead of just being like, whoops, my body will be like, catch it or you'll die, and I'm like that. So you'll get to see it soon enough. It's my reflexes. They're fast, but they're horrible. So back to this. I go outside. I've got on a dark shirt. Turns out the electrons in my dark shirt get excited. They go up in energy level when the sunlight hits them. But they're not stable up there. So what do? They fall back down. When they fall back down, what do they release? Energy in the form of what? Heat. So now my black shirt is releasing heat. And I'm touching it with my arm. So how does it feel? Hot. When I go out and I touch my black car, I'm feeling falling electrons. Like, ooh, those electrons are falling a lot. That's the second day you try that one. All right. I've got the little stars on my ceiling. I shine a light on them. What do you think's happening when the light hits those? What are the electrons doing? Yeah, they're getting excited. They go up to a higher energy level. They might bump up a couple of energy levels. I don't know how high they go. And then you turn off the lights. They're not stable up there, so they start falling. But instead of giving off heat, what do they give off? Light. You get a glow stick. Chemical A's in some capsule, chemical B's all around it. You crack it, they start mixing together. The electrons go up in energy levels, but they're not stable, so they fall. And now it glows. All right, you're like, that's fine, Mr. Cotton. We're in biology class. What does this have to do with biology? Okay, so here's the part that gets a little bit weird. And by the end of the cellular respiration and photosynthesis unit, this will totally make sense. For now, if you're generally following the idea, you're in good shape. So don't feel like you have to understand every bit of this. This is just like, I'm trying to get you to see why energy levels matter. So, let's say I've got a dark green shirt, and I go outside. Does my shirt do photosynthesis? No. But a green plant does. So what's the difference? When I go outside in a dark green shirt, sunlight hits the electrons, they go up in energy levels. Then they're not stable, so they fall back down, they give off heat, and I go, my shirt is warm. But if I'm a plant, in a plant, chlorophyll is unique. When the sunlight hits electrons in chlorophyll, those electrons go up in energy levels. But then before the plant lets them fall, the plant will store those electrons. Let's say it's an apple tree. They'll store those electrons in an apple. I'm not making this up. Then you eat the apple, and you steal those electrons. This is in your body. This is you. You'll take electrons from that apple, put them right here. Are those electrons stable right there? No, so what do? They fall, and they release energy. And that's how you get energy from food. Falling electrons. So, I got some electrons. I ate an apple. I got some electrons. I use the energy. So now they fall down to like lower energy levels. Then I get rid of them by peeing. I pee out the electrons on an apple tree. I pee on apple trees. That's just the kind of guy I am. So then that apple tree steals the electrons from my pee. This is why you have to water plants. They steal the electrons from my pee. They're at low energy levels. We zap them with sunlight. We build an apple. I eat the apple and steal the electrons. Let them drop in energy levels. Pee on a tree. It builds an apple from my pee. It then takes those electrons, hits them with light to re-excite them. This is the cycle of life. This is how all calories work, whether you're eating carbs, lipids, proteins, whatever. That's how you get energy from food. How do you get energy from food? By stealing electrons from food, putting them on a ring that's high, that they're not stable at, and then when they fall down, that's how you get energy. Every thought that you are having right now is because electrons are falling. every movement, every heartbeat, whatever. It's because electrons are falling. Isn't that just weird as hell? So bizarre. Real quick, I'm going to throw in one last thing. This is going to seem a little bit random. What's a covalent bond versus an ionic bond? Think back. Again, I know if you're a senior, it's been like probably 3 years since you've had chem, unless you took AP Chem. Yeah.
Well, ionic is between two elements with a negative and a positive charge, and a covalent is one between two polar.
True. Ionic, there's that kind of like, I don't have it on here, but that little stair-step thing. In general, if you have stuff over here bonding with stuff over here, it's ionic. And they traded something. What were they trading? Electrons. If it's covalent, they're sharing electrons. So bonds are made out of electrons, right? Okay. So back to my analogy of just trying to understand the big picture. Watch this. Hang on, I need more pens. I've got a whole drawer of pens over there. It's what I get if any. You know, sometimes students will give you like something at Christmas or whatever, like a small thing. I get pens. Quick aside. I'm not obsessed with expo pens. I do a lot of expo pen analogies, and then my students are obsessed with them. It's not me. So if you're like, Mr. Cotton, is that an expo pen holster on your wall? My answer is, hell yes it is. It was supposed to be. One time in class I said what I need is like one of those deals like when you've got like an M60 and you got like all the bullets or whatever. But they didn't calculate for my girth, so it won't quite work because I'm huge. So a student made this. She didn't buy it. She's like, it took me forever to stitch that. I was like, holy crap, I can't believe you made it. An expo pen holster. I messed that up. Expo Man, I didn't create that comic book character. As a student. These are students, not me. That's an expo dry erase marker. A whole lot of biology on the back, by the way. Pretty impressive. So it's not me, it's you guys. But I do a lot of expo pen analogies. Okay, so back to the topic at hand. All right, think for a second. Again, you're not having to write any of this down. I'm just trying to get you to see like how this fits into biology. And it will matter as the year goes on, but you don't have to know it at this exact moment. Do you guys remember seeing that molecule in your 9th grade bio class? Do you remember what it was called? Glucose. Yeah, it's a carbohydrate. It's an ose, so it's a carbohydrate. Okay. So back to my energy level thing. These 6 expo pins represent those 6 carbons. So forget all the rest of that for a moment. We're just going to track the carbons. So here's 6 expo pins, 6 carbons. What's holding all these C's and H's and O's together? Like chemically, what bonds carbons together? Yeah, I could have an ionic bond or a covalent bond. It's a covalent bond. And what were covalent bonds made out of again? Electrons, sharing electrons. So electrons. So here's a carbon. I want it to stick to this other carbon, but it can't right now. So what do I put in there? Electrons. I promise this will be cool, so hang with me. I realize right now we're kind of bouncing all over like I said we would, but hang with me. Here's another carbon. I bond it together. I'm building glucose. And then I'm going to eventually convert it into another sugar called fructose. There's an R in that word. And fructose is in fruit, so it's fruit sugar. But anyway, we'll just follow glucose. So here's my glucose. There you go. So what are these pen caps representing that was joining everybody together? Yeah, electrons in the chemical bonds. Okay, so I'm going to eat this apple. So this came from an apple tree. This is the sugar in an apple. So here we go. Impressive, I know. It was just an illusion. I didn't really eat them. It just looked like I ate them. Now, here's what my body's going to do. My digestive system. The whole purpose of my digestive system is just to steal electrons. So it's going to steal electrons. But what were those electrons doing before I stole them? What was their job? Like 5 seconds ago. Bonds, holding all these carbons together, right? So are the carbons held together anymore? No. So do I need these anymore? No, all I want is the electrons. So carbon dioxide, I breathe that out. That's why you breathe out carbon dioxide. You're breathing out whatever you ate this morning. Now, my body steals these electrons. It will then go, and inside of my mitochondria, it will drop off those electrons right here, and here, and here, and here, and here. Are they stable up there? No. So they fall and release energy. And that's how I get energy from food. I then take those spent electrons, and like I was saying before, I breathe in oxygen, attach electrons to it, convert it into water, take a piss. The plant says, thanks for the piss. It takes those electrons, energizes them, breathes in the carbon dioxide, and builds another apple. That's the circle of life. We just did the carbon cycle, the oxygen cycle, and the water cycle all at the same time. That's how all energy in life works. Right? When photosynthesis ends, isn't that kind of it for the planet? So this is like the cornerstone of life. It's just electrons. Your digestive system, its only purpose is to steal electrons. Your respiratory system is just getting rid of electrons. All right. I know that's a lot all at once. And you're like, I don't even know what's going on right now, Mr. Cotton. Like I said, we're going to bounce around and it'll be random in the beginning. Okay, so the important thing about energy levels, when electrons go up in energy levels, they're absorbing energy. When they fall down, they're releasing it. If I can somehow send them up there and not let them fall, I'm storing energy. Just like if I can hold these up high and not let them fall, that's storing energy, potential energy. All right. I know that was kind of weird, but how y'all doing? Pretty good, pretty good. Okay, mostly thumbs up. All right, you may or may not be lying. It's a little bit tricky because of masks. I can't read your facial expressions. I'm sure you've had teachers tell you this before. But kind of like me, if I say something, you're like, is he being sarcastic or not? Like, you can't always tell from my face. Okay, so if you're following along in your notes, skip down to where it says, we'll ignore isotopes for the moment. Skip down to where it says bonding. Right there. So bonding, 2.2. So there's covalent bonds and ionic bonds. We mentioned those just a moment ago. So for an ionic bond, and by the way, probably halfway through next class is when this will start to feel like a bio class and not a chemistry class. So in case you're wondering, like, how long does the chemistry go on? About halfway through next class, it'll feel like a bio class. So we have ionic bonds and covalent bonds. And with ionic, we said that we like, I guess you could say, give and take electrons. Yeah, trade electrons. Careful if you say trade, though. It's not like I give you one and you necessarily give me one back. It's like somebody's giving and somebody's receiving. But I don't like give and receive, if that makes sense. So you can write trade, but just make sure you realize it's not like I give you an electron and you give me an electron. It's not like a one-to-one trade or anything. And then in covalent, you share electrons. All right. So real quick, let's look at the periodic table and see why it is that when stuff over here bonds with stuff over here, it's usually covalent. And when stuff over here bonds with stuff over here, it's usually, but not always, ionic. All right. Switch views for my camera. Okay, now, think back to chemistry. What was the charge of everybody in this column? Do you remember? This column had a charge. What was the first column? Everybody here was a +1. What was everybody right here? +2. What about the noble gases? They're totally neutral. They don't have any charge at all. What about this row or column? -1, -2. You kind of remember that a little bit? Sodium has a +1. Chlorine has a -1. So sodium and chlorine will go together 1 to 1. Magnesium has a +2. Chlorine has a -1. So for them to go together, for every one of these, since it's a +2, I need a couple of these since they're -1. So magnesium chloride would be like MgCl2. Kind of coming back a little bit? Okay, that's an ionic bond. When stuff from here bonds with stuff over here, that's ionic. That's actually what you spent most of your time in chemistry talking about, was ionic bonds. You had ion quizzes and everything else. Unfortunately, the bonds that we talk about the most in biology are covalent bonds. And you didn't learn a whole lot about covalent bonds. Okay, so covalent. Covalent is if we share electrons. All right, so who was it that was stable and never reacted with anything again on the periodic table? Yeah, the far column, the noble gases. Okay, so let's say that I am fluorine, kind of like potassium fluoride in your toothpaste. So let's say that I'm fluorine. How many rings will I have around me if I'm doing like energy levels? 2, because fluorine's in row 2. 1, 2. Here's another ring. How many electrons does it have in its outer ring? 7. I know that because 1, 2, 3, 4, 5, 6, 7. If I'm counting on the periodic table, it's in column 7. I realize you couldn't see that. So 7. 1, 2, 3, 4, 5, 6, 7. So, is fluorine stable? No. Here's the part that's going to bother you. Is it neutral? Yes. But is it stable? No. So think about it. Fluorine has a 9 above it. So how many protons does it have? 9. So it's got 9 protons. How many electrons does it have? 9. So is it neutral or does it have a charge if it's got 9 and 9? It's neutral, so it's totally neutral. However, is it stable? No. What does it need to become stable? 1 more electron. The rule is when your outer layer is full, you are stable. So right now it needs 1 more electron. Or it could either gain 1, or how many would it have to lose to have a full ring? It'd have to lose 7. So I could gain 1 if I have 8 out here, or I could lose 1, 2, 3, 4, 5, 6, 7, and now I've just got my inner ring that's full. So what's more likely, shuffling around 1 electron or 7? 1. So out in nature, almost always, it's going to gain 1 electron. There you go. It's going to gain an electron. Now, it just gained an electron. So how many electrons does it have now? 10. So now it has 9 positives and 10 negatives. So what is its charge? -1. That's why fluorine in this column has a -1. Same thing for chlorine. Now, chlorine will have 3 rings around it, but it's going to always gain 1 electron. That's why everybody here is -1. Why is oxygen a -2? Because to become stable, it's got 8 protons, 8 electrons. But to become stable, it's going to gain 2 more electrons. So it's going to be a -2. So that's why this is all -1, because they want to gain 1 electron. These guys are all -2 because they want to gain 2. If I'm sodium, I could gain 7 electrons. 1, 2, 3, 4, 5, 6, 7. But what's easier? Losing 1. If I just get rid of 1. So if I'm sodium, I look like this. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. By the way, if you're like, man, I can't wait till the chemistry's over, we could be doing stoichiometry. And we won't, so there you go. So sodium looks like that. So if it can just lose that one electron, won't it be stable? Yes. Hey, wait a second. Doesn't fluorine want to gain one? Doesn't sodium want to get rid of one? And that's why sodium fluoride exists. Because he can give his away, he can receive it. There you go. Since somebody's giving and somebody's taking, that's called ionic. All right, we're almost done with the randomness. What about, though, if I have somebody from over here and somebody from over here? Like, let's say that I had somebody in this column and they wanted to gain electrons, and somebody in this column that wanted to gain electrons. Then what? Like, pretend that I have one candy bar and two kids, and they both want it. What do I have to do with the candy bar? Yeah, I've got to make them share. So in general, when you have stuff over here, they're wanting to gain electrons to become stable. The ones over here are wanting to get rid of one or two. These guys are wanting to gain one or two. So generally when stuff over here bonds with stuff over here, it's covalent. Hydrogen's annoying because hydrogen can act like it's here. Hydrogen can also act like it's right here. So hydrogen's kind of tricky. So turns out for you and I, we're made almost exclusively of chomps. And I'll write that out so you can see what I mean. Chomps. CHONPS. That's about 98.5% of what you're made out of. So out of the entire periodic table, you're pretty much just carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Okay, now we're going to talk about covalent bonds, and then we'll be done with random chemistry stuff. We'll still have chemistry stuff, but it'll like flow. Okay. So back in your chemistry class, did you guys ever do Lewis dot structures? They would look like this. Carbon. How many electrons does carbon have in its outer shell? 4. Yeah, it's got 6 total, but its outer shell has 1, 2, 3, 4. We're always looking at the outer shells because that's what determines if something reacts. So we should probably give that outer shell, that outer ring, a special name. What's that outer ring of electrons called? Yeah, the valence shell or the valence layer. So carbon has 4 valence electrons. 1, 2, 3, 4. If I go ahead and tell you that carbon just always bonds covalently, I can't tell you why, but it essentially always bonds covalently in nature. You're like, all right, it's got to share electrons. Let's say it's going to form some covalent bonds with hydrogen. How many electrons does carbon need if it's going to gain electrons to become stable? 4. It needs 1, 2, 3, 4. Then it'll be stable like this noble gas. So it needs 4. It's got 4, it needs 4 more. What about hydrogen? How many does hydrogen need to become stable? Just 1. So let me go back. Carbon is right here on the periodic table. I've got to move 4 spots to get to the closest noble gas, so I have to gain 4 electrons. Hydrogen's over here on a periodic table. So for it to get to its closest noble gas, it has to gain 1 spot, 1 electron. Okay, so now I've got carbon and I've got hydrogen. How many electrons did hydrogen need to gain again? 1. So they can form a bond. Covalent bonds are always solid lines. You'll always draw them as a solid line, no exceptions. How often do you get to hear always and no exceptions in like a science class? Not very often. So they're always a solid line. Now, the electrons now count as both of them because they're sharing. It's kind of like if you and I are brother and sister or brother and brother or whatever, and we share a car, it's kind of both of ours. So now, how many electrons does that hydrogen have? 2. Is it stable now? Yes, so that hydrogen is stable. How many electrons does the carbon have? 5. 1, 2, 3, 4, 5. Is it stable yet? No, it needs a total of 8. So does this exist in nature? No. What if there's another hydrogen around? That hydrogen is stable. Now how many electrons does this carbon have? 6. Does this exist in nature? Nope. Almost. Now carbon has 2, 4, 6, 7. We're close. That doesn't exist in nature. And then finally, are all the hydrogens and the carbon all stable? Yes. So is that a thing? Yeah. Does anybody know what that's called, by the way? CH4? You'd study it some in like an environmental class. If you ever took APES, maybe. You might have had a friend named Brian Gaynor. He wasn't really a friend, but he lived across the street. And when you're young, you just kind of like hang out with whoever lives nearby. So, cool guy, but like as soon as you move out of the neighborhood, like you never talk to that person again kind of thing. So you might have had a friend named Brian Gaynor. You thought he was an intelligent kid. Then one day he comes over and he's like, watch this. And he lights a fart. And he's like, you want to try? And you're like, no, man, I'm good. That's methane. It burns blue when you light it, and it's in farts. You always hear about how like cow farts are causing global warming and people farts are causing global warming. It's the methane. So, all right, so that's methane. Let's look at a couple more chemicals here and see what we can see. There we go. All right. Does it look like there's a rule on how many bonds carbon always forms? Like I'm just looking at all these. 4. It might form 4 single bonds. What's that probably called? Double bond. That's a double covalent bond. They're solid lines, so they're covalent. It can form 4 singles, or this one has 2 doubles. That still adds up to 4. That carbon has a triple and a single. Still adds up to 4. So out in nature, carbon always forms 4 bonds. What about hydrogen? How many does it look like hydrogen always forms? 1, because it wants to gain 1 more electron. So no matter where it's at, hydrogen is always going to form 1 bond if it's going to be stable. And then what about oxygen? Looks like oxygen's pretty much always 2. Here's a single. That one's got a double, that one's got a double. So if we look at chemicals, what we'll find, that got blurry on you guys on the camera. What we'll find is this. Carbon always forms 4. Hydrogen always forms 1. Oxygen always forms 2 bonds. Now, you're going to see a bunch of chemicals throughout the year, so you'll eventually just know it but memorizing that is useful. It does save you time. Eventually, we take time tests, because we're in an AP class. So actually, all of our tests will be timed. That's one of the ways I'm going to mitigate cheating with kids at home. It's going to be interesting. But basically, carbon always forms 4 bonds, hydrogen 1, and oxygen 2. All right. One last random chemistry thing, and then we're out of the randomness. So you've got pretty much all the background chemistry you need, almost. Skip down to where it says water. So we're actually going to be explaining hydrogen bonds along the way, but we're going to do it with water. We'll come back and get to van der Waals forces. Van der Waals forces, I think you've only heard of those if you've taken AP Chem. I don't think that you get into that at all in Chem 1. So skip on down to water. Okay, here's the cool thing about water. At first, you might go like, that seems like a lot of information about water. Yes, it is. This is not your current biology book. But here's chapter 3. Water. All of chapter 3 is water. It's not a part of chapter 3. All of chapter 3 is water. Water and the fitness of the environment. We're talking about water. Water chemistry. Water chemistry. Water chemistry. all of this, page after page of water. In a college biology class, they pretty much always have either a chapter or a really large section on just water. So, water itself is important, but the chemistry you learn when you learn about water, we apply to everything. We'll learn in the next unit that cells just build themselves. Nothing even has to put them together. If you take phospholipids and put them in water, they automatically make cells. Why? Because of water chemistry. So, water chemistry. Water chemistry is interesting because not only does it kind of explain a bunch of cool stuff, but it also kind of like shows how biology works overall. So in water chemistry, I'm going to teach you like one or two things, and then after that, the third thing will just make sense. And the fourth thing you'll be like, oh, well, of course that happens. Well, of course that happens, and that, and that, and that. That's how this class should feel from now on. We'll come in, I'll be like, hey, observe this or notice this. What did we learn? This. Observe this or notice this. What did we learn? This. Okay, well, if those two things are true, what would happen in this situation? And you're like, this. Well, if those three things are true, what would happen in this situation? This. And so you kind of have to like learn or memorize one or two things, and then everything else should just be logical afterwards. That sort of makes sense. Almost like this country did this country did this, and now you can see how the war escalated. It's just very logical. This one bombed this one bombed them back, and then now you see how it all worked. So, with water chemistry, we start off with the shape of water. Was that a movie? I think it is. I think it won a bunch of awards. I saw that. It's the worst movie I've seen since Gangs of New York. Did y'all ever watch Gangs of New York? I swear it's still playing. Like I watched that in a movie theater. It's the longest movie I've ever seen. That also won awards. I basically can't watch anything that's like highbrow, I guess. The Shape of Water was horrible. It starts off pretty good, and then this lady ends up like having sex with a fish. And it's not implied. In the beginning, it seems like there's something, there's a hidden, there's some sort of animal, some sort of beast, and she falls in love with it, and then all of a sudden you're like, looking over at my wife, and I'm like, are we watching bestiality right now? Like, what is this? And they're like, let's nominate this for awards. It was nominated for I don't even know how many awards. I don't know if it won or not, but, you know. I guess he's a misunderstood fish. It's a metaphor. I don't know. So anyway, my wife calls it quirky, my personality. Not quite to the point of being weird usually, but I don't know. So the chemical structure of water is bent. That's like the official name. So again, depending on your chemistry class, you might have had to learn like shapes. They called it Vesper theory, and they had weird names like trigonal bipyramidal and trigonal planar and crap like that. Well, this is the official name. So like if you were in a college biology class and they're like, what is the shape of water? You'd be like, bent, and they'd be like, exactly, +1. It is called bent. You're like, all right, fine, whatever, cool. Number 2, the next thing that I have to tell you, and then after that, this will explain a lot of stuff, it'll just kind of flow logically, is this. Oxygen has a high electronegativity. Save that one for the third date. Oxygen has a high electronegativity. You don't have to know the number, but I like to feel smart, so I'll tell you what it is. It's 3.5. Hydrogen does not. Hydrogen has kind of a low medium electronegativity. It's like 2.1. Oxygen has a high electronegativity. Hydrogen has a low to medium electronegativity. If you want to think of it this way, 2.1 to 3.5, that means this is about 75% higher. All right, so does anybody remember what electronegativity is? It's hard because you learned it in chemistry and then you learned it in one unit and then you likely never used it again. Does anybody remember what it is? Based off the name, what do you think it's kind of related to? You're like, I don't know, negative electrons, I guess. Yeah. So if I look at the periodic table, come on, there we go. If I look at the periodic table, there was a unit in your chemistry class where you would learn trends. Your teacher would be like, as we go to the right on the periodic table, this goes up or this goes down. As we go to the right and up, or as we go to the right and down, we notice these trends. Okay, one of them was electronegativity. Electronegativity goes up as you go to the right and up. Here's an electronegativity periodic table. Cool, it's coming through pretty good. So what's the most electronegative thing up here? Fluorine. Who's in second place? Oxygen. So oxygen is the second most electronegative thing known to man. Hydrogen is over here at like a 2.1. Okay, so any ideas what electronegativity is? Based off of this chart, you might be able to figure it out. Not based off of something from years ago, but based only on stuff that we've mentioned today in class. You might be able to figure out. It's hard. What do you notice about the left side in general versus the right side regarding electronegativity? Do what?
The right side has more covalent bonds.
That's true. When right is bonding with right, that's more covalent bonds. That's true. What else about just electronegativity? Where is it higher, on the right side or the left side? The right side. So what do you think electronegativity might be measuring? What does oxygen do? Oxygen has a high electronegativity. So what does oxygen do more than, say, hydrogen?
Form bonds for electrons.
Yes, I'm going to change your wording slightly. It's hogging electrons. It's attracting electrons so that it can form bonds. I'm just going to kind of switch up the order. So basically, isn't everybody over here wanting to gain electrons to become stable? Aren't the ones over here not wanting to gain? So electronegativity, this is the Mr. Cotton definition, is just how strongly you hog electrons. That's super important. Electronegativity is how, let me switch views for my home crew. So, or my video crew, how strongly, I just misspelled strongly, how strongly we hog electrons. Now in a chemistry book, they'll say like attract. You don't hog stuff if you're in a chemistry book. So how strongly you hog electrons. Okay, so those are the two things that we need to know about water. After that, everything will explain itself. So here we go. What kind of bond was this again, if it's a straight, solid line? Covalent. What was the definition of a covalent bond? Sharing electrons. So is oxygen and hydrogen right there? Are they sharing electrons? Yes. That's a covalent bond. Okay, cool. Are they sharing electrons equally? No. Who's hogging the electrons more? Oxygen. Because oxygen is a bigger electron hog than hydrogen. Okay, so think of it this way. Here's a water molecule. And again, we don't know that electrons orbit like planets, but I've got a marker and a whiteboard, so what you going to do? If they had equal electronegativity, then the electrons would be doing this. Spending equal time around everybody. But they don't. So where do the electrons spend most of their time? Around oxygen, because oxygen is a bigger electron hog. So instead, water looks like this. Here's how water shares electrons, or here's how oxygen shares electrons. Are they still technically sharing? Yes, but it's kind of like, you know, I've got a son and he's older now, so he's a little bit more civilized. But when he was a kid, if we were like at the movie theater trying to save $1 and it wasn't COVID-19, then we just like get one big drink and we would pay for the drink at the theater. But we'd get one big drink and share it. And the way that he shared it, he'd be like, you know, like that. And then I'd get like a little sip. You know, he shared like oxygen shares electrons. That's what I told him. I don't think he got it. But anyway, so what that means is this. I've got a water molecule. Around the oxygen, because the electrons spend so much time around there, there's a slight negative charge around oxygen. There's a slight positive charge around the hydrogens. And that's called water is polar. What does polar mean? We use it in English, and then we also use it in like a physics class. We use it in just the English language. What does polar mean? If you and I have polar personalities. Yeah, opposites, two states. Like on a magnet, you have north and south pole. You know, obviously, the Earth has a magnet, north and south pole. In psychology, bipolar is where you go through stages of mania where you're like, I'm going to start 2 businesses. Look out, world, here I come. You're confident, you're ready to get out there. And then what's the opposite of that? Depression. Then you're like, I can't get out of bed. I don't know that I have any reason to do anything. I suck. So bipolar is like swinging between moods of high and low, basically. So polar means opposites. Does water have some opposites? Slight negative and slight positive. Okay, so water's polar because it has slight negatives and slight positives. In chemistry, anytime you use the word polar, you're always meaning opposites. It might be a positive and a negative, or a slight negative and a slight positive. Okay, so now, let's kind of backtrack this a little bit, see how we got here. Water's polar. What does that mean? It has some opposite charges. Why? Well, because oxygen hogs electrons more than hydrogen, even though they're sharing. Okay, fine. What if I had some water molecules next to each other? Here's option 1. The water molecules could be like that. Here's option 2. This is option 1. That's option 2. Which one of those is right? Option 2. What's wrong with option 1? Why won't that happen? Huh?
Yeah, if both of the hydrogens are positive, they would repel.
Yeah, that slight positive and that slight positive would repel. So that water will automatically move. If I do this with my water, I swirl it around, they might be like that for a second, but then as soon as I'm done, that water molecule moves over here. So it's regular. You think that it's random in there, and it's not. They just all like fall into place like magnets. You can, you know, rummage them around and everything else, but once you stop, like they're going to all stick together in a certain formation. So that means that that water molecule is attracted to that water molecule. And that attraction is called a hydrogen bond. And hydrogen bonds are always represented with dotted or dashed lines. Covalent are always solid lines. Hydrogen bonds are always dotted or dashed lines. Okay, so between 2 water molecules, I have a hydrogen bond. Why? Well, because each water molecule is polar, meaning it has slight negatives and slight positives. Why? Because oxygen hogs electrons more than hydrogen does. Do you see how this thing sort of leads to this thing, which sort of leads to this thing, and then we can kind of back up like, this happens. Why? Because of this. Why? Because of this. That's how biology should be all year long from now on. It should always be that, like, once I know these 2 things, the next thing just kind of makes sense. All right. So doesn't that mean that water molecules stick to other water molecules? Like if I had another water molecule over here, wouldn't he form hydrogen bonds with this guy also? Like that? He would. So that leads us to the next thing. Cohesion. Cohesion is when chemical X sticks to chemical X. Like water to water or blah blah to blah blah. Water sticking to paper towel, that's different. That's not cohesion. So, water is cohesive, meaning water sticks to water. Why? Because between water molecules, I have hydrogen bonds. Why? Because each water molecule is polar, meaning it has slight negatives and slight positives. Why? Because oxygen hugs electrons. It's a lot of stuff, but again, that causes this, causes this, causes this. Adhesion. That is when X sticks to Y. So we'll get to do some analogies here in a second, some like things that you find in nature. Okay. This will probably be the last thing. I'll give you a couple analogies, and then I'll check and see if Yonda sent out a link for TCTV. Adhesion is when X sticks to Y. So here's a paper towel. Let's say that in my hand, or let's say that I dump a bunch of water up on the counter. Well, first of all, I dump water on the counter. So let's say here's the counter. When the water gets to the edge of the counter, when it gets to the edge, there's a little bitty stream, almost like a peninsula of water. When that little bitty peninsula of water gets to the edge of the counter, does it fall off or does it tend to like pile up along the side first? Like how many of y'all have had like the water's kind of piling up on the side and then you touch it and then all of a sudden now it all falls off? It actually piles up first. Probably in 7th or 8th grade and maybe again in 9th grade, you got a penny and a water dropper and started putting drops of water on there. You'd think you could get like 3 or 4 drops, but instead you got like 25 or 30. And when you looked at the penny from the side, it was ridiculous. There's your penny from a side view, and you had like this bubble of water that was about 2.5 times taller. Why aren't those water molecules falling off? Because water is cohesive. It's hydrogen bonding to itself because it's polar, because oxygen's an electron hog. So these guys are holding on to these guys, cohesion. Okay. Now, what if I've got water on the counter and I take a corner of a paper towel and I put it in there? Won't the water go up against gravity, up the paper towel? Like an inch? I don't even know how many like billions of molecules high that is. But it goes up like an inch. If instead I had wax paper or plastic, pretend that I dipped the corner of this in water, will it climb up the plastic bag or will it climb up wax paper? Why not? What's different about the wax paper versus the regular paper? Like, I know that one has wax on it, but like, what's different? Or if I had like a laminated paper, when I dip that in water, it doesn't soak it up. This one does. What chemical property do I know about this for sure? It absorbs. Why? Water's adhering, it's sticking to paper towel. So what do I know about paper towel? Water does not stick to wax paper, so what do I know about wax paper? Yes, wax paper is nonpolar. This is polar. This is covered in tons of pluses and minuses. So here's my paper. So as soon as I dip it in water, the slight negatives are attracted to the slight positives. Then the slight positives are attracted to the slight negatives, and it just climbs up. And then doesn't it bring all the other water with it? Cohesion. It drags everybody else along. Think of it this way. Pretend that this wall over here is a piece of white paper. Not wax paper, just plain old like paper towel. and I'm a water molecule. And you all are water molecules. So when we're all next to each other, this will be the last thing, and like I said, I'll check to see if we've got TCTV now. So we're all water molecules. What happens when I get close to one of you guys? Don't we stick to each other? Cohesion. Yeah, we'll form hydrogen bonds because we're each polar, because oxygen hugs electrons. Okay, now, what happens when paper towel gets dipped in us? So we're all in water, you know. Here we are. We're all water molecules. And now, this entire wall is paper. It gets dipped into us. Isn't my head, so my head's the oxygen, my hands are the hydrogens. So isn't my negatively charged head attracted to that positive? So I just like smash my head against it. I'm like, pow. And when I do that, this hand is positive. It's attracted to like this negative. So it's like, pow, and that pulls my head off. And then this one's attracted to this negative, pow. And before you know it, I'm just like, all the way up the piece of paper, because I'm adhering to the paper. But I'm also cohesive with you guys, so don't I drag all of you guys up with me? That's how a paper towel works. Now, on one hand, you're like, what'd you learn today? And you're like, I learned how a paper towel works. And people are like, sucks to be you. But this will explain all kinds of things in biology. If I have wax paper is neutral. It doesn't have positives or negatives. So if I dip that in water, nothing happens. Let's say I make a batch of brownies. I want to leave them out on the counter to cool, but I've got like a dog, a golden retriever, because I do. And if I did that, I might end up having like a dog hair land on there, and that's disgusting. So I want to cover it, right? So I could cover it with regular paper towel. Put it on there. It dries. I come back 20 minutes later. When I pull off the paper towel, what's going to happen with my brownies? Isn't the paper towel going to be like stuck to the brownies? Won't it rip it apart? So instead, I put wax paper on there. When I remove the wax paper, what happens? Doesn't stick. This is hydrogen bonding with my brownies, and this is not. So this causes this, causes this, causes this, causes this. That's how we want to learn biology. Don't just memorize 10 random facts. That leads to that, leads to that, leads to that. Yeah, you have to memorize names, cohesion, adhesion, but it should kind of all follow like you're watching a movie, the movie of life. All right, we're done for today. I'll check and see if we got some TCTV.